Second case, I don't even need to do it, right? Ask yourselves, try to tell me, if in this case, in the second case, we still do not have the surface current density, but in this case, mu, we have a very, very good magnetic material. So mu is very large. How large? Let's say 1,000, 1 million. Can you come up with your own conclusion? What is going to happen when mu is very big? In the extreme case, when mu is really infinite, and this is positioned in vacuum, so mu r, right? Mu r is infinite. What is going to happen? Can you see, do you need to go over the entire process? Once you don't have the surface current density, H1T is always equal to H2T. So you're not changing the tangential component, right? The fact that now you have a very large mu is only affecting your normal component. So now mu is much, much bigger than mu2, right? This is mu0 and this is mu. It is going to force your H2n approaching to infinity, right? H2n now is approaching to infinity. So in this case, the second case, well, we still have H1, still have mu, mu0, but now the case is H1T, which is still equal to H2T. Dot, 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 dot. But now the fact is H2n is equal to mu r H1n. And this guy is approaching infinity. So this is forcing this H2n going to infinity. So tell me, what is the resulting angle theta 2? In this case, 0. Yes, thank you. Because you don't really need pen or pencils. You don't even need calculation, because in the first example, we already know that theta 2 has to be smaller than theta 1. When mu is close to mu0, it's equal, right? As you increase mu, this angle would always be reduced. Until when? Until your mu is extremely huge. So basically, this is your H2. H2 is pretty much, in this case, entirely occupied and determined by the normal component. Well, even though you still have this tangential component. But infinite compared to this is nothing, right? So in this case, theta 2 is really approaching to 0 degrees. No matter what angle theta 1 is, remember, if you have a very huge mu, no matter what angle you have, for incidence, your angle coming out is always 0. Think about it. Is this practical? Go back and think case number 3. Well, you probably never encountered these two examples, okay? Because in our daily lives, we don't deal with magnetic materials as often as we deal with dielectric materials. But some example we did see in the past is this case, okay? This is an interesting case, and now you have the ability and sufficient knowledge to understand, well, if we do have surface current density, what is going to happen? Before I perform the analysis, I want you to take a guess. Up to now, case 1 and case 2, whenever you don't have the surface current density, your angle coming out, well, as long as your initial material has a higher mu, your angle coming out has to be smaller, right? This is an important finding. When you don't have surface current and your mu for the initial material is larger than the second material, your angle would be smaller. Now, as you increase mu, your angle is sweeping from equal to theta 1 to the surface normal, making theta 2 approaching 0. But then you should be asking yourself, can it be possible that this angle, theta 1, becomes negative? Well, in these two cases, your incident field and your exiting field will be lying on the different side of the surface normal, right? For this one, your incident field is on the left-hand side, your exiting field is on the right-hand side. In this case, when you have a very huge permeability, your exiting field is exactly on the surface normal. But can you make it so that your exiting field lies on the same side as your incident field? From our current analysis, this is impossible because, as we said, well, this only approaches to 0, right? So this is impossible, and for this definition, this theta 2 is negative. Okay? Now let's take a look for case number 3. I'm trying to illustrate the importance of a provided free current surface density. Okay? Now that Js is no longer 0, so this is like a solenoid, right? We talked about solenoid in the very beginning, and we also talked about this ring, right? This ring and having a cut. That's also like a solenoid. So case number 3. Case number 3, Js is not equal to 0. So I have my interface. I still have mu and mu 0. Okay? I have my surface normal. But let me just plot the free current densities explicitly. So in this case, I'm assuming this interface is having currents flowing out into your eyes. Okay? I still have my H1 field with incident angle theta 1. So I can safely say, well, this is my H1T. But due to the presence of a non-zero surface current density, I cannot just say, oh, this H1T is equal to H2T. No longer. Why? Here, right? H1T minus H2T is equal to JSN. with the presence of a provided free surface current density and now normal to this cross-section, I have to be careful, right? According to this equation, let me write H2T. Let me use the right color. H2T can be written as H1T minus JSN. Right? I'm only moving this guy to the right and this guy to the left. What does that tell you? That actually tells you when your applied surface current density is huge enough, your H2T can indeed reverse its direction. In the previous two cases, H2T are all in the same direction as your H1T, and they also have the same magnitude. Okay? With the presence of your surface current density, H2T does not need to be equal to H1T, but more importantly, its direction can reverse sign, right? You can, if this is big, this is becoming negative. What does that mean? It means you might have H2T, right? Reversing the sign. Once your tangential component has a reversed sign, no matter how big your normal component is, what did I use to illustrate? Okay? This is my H2N. So the real magic in achieving a negative angle coming out relies on the fact that H2T has to have a reversed direction. And that is only possible by the help of a non-zero surface current density, and you have to be big enough. So this is really angle dependent, right? H1T is H1 times sine theta. So this is really angle dependent. Even for the same material, not all the magnetic field lines can come out with a negative angle. It is angular dependent because your applied current density, assuming it's fixed. Okay? So in the end, your field coming out, in this case, would have a theta 2 smaller than 0. By definition, right? Your exiting angle, if it's on the same side as your incident angle, this takes on a negative sign. Why do I care about this? Do you still remember? We talked about solenoid of finite length, and then we can have the so-called leakage fields, right? This leakage field comes out with a negative angle. You cannot have this negative angle without the free surface current density. Better yet, we just talked about this on Monday, right? We have this magnetic core and we wind a lot of wires. So basically, this is like a solenoid, and we talked about this leakage flux. Leakage flux is having field lines coming out, right? But if you pay attention to how this leakage flux were plotted, they always form a self-closed loop, meaning that your incident angle here, right? This is your material vacuum interface. The angle coming in, angle coming out are on the same side of the surface normal, meaning your exit angle is negative. Why is that possible? Because you have lots and lots of applied free current density. Okay? So I'm hoping by all this explanation, you feel the importance of boundary conditions, and now understanding boundary conditions really help you to appreciate the fact of this self-closed loops called as the leakage flux. Why are they possible? If you don't have this free current densities, all the fields can at most do this, right? Do this. So your incident angle, positive, exit angle, positive, meaning the exiting field are always on the other side. You cannot generate this type of field lines. All right? Final note. What about on this surface? We only talked about the side surface, right? Imagine this is a magnetic rod. So your applied field is coming this way. We talked about this one being able to give rise to the leakage flux. But in the end, this is like the cut, right? Somehow this rod needs to end in space, so you have another surface. This is a side surface. This is an end facet. This surface is like this cut, right? If you still remember, on Monday, we talked about the basic assumption is we don't have leakage flux, but then I also made a second assumption. All the field lines inside the core are penetrating this gap and re-enters the core. Do you still remember? Oh, that is a very strong assumption. And no one, none of you challenged me the possibility of I'm drawing the cross-section of the toroid. So this is mu, this is the gap, this is mu. We assumed all the field lines come out, go into the gap, and re-enters. Okay? None of you challenged me, is it able to do this? One of the field lines come out and start to circulate by itself. So the field line does not really go back into the core. Is it possible? Take a look at this. So imagine, this is our solenoid, right? This is our solenoid, and we have a magnetic core at the center. So we have externally applied magnetic field, and we also generate induced dipoles. So remember, for this facet, the applied free currents are on the side surface. You don't have applied free current densities along this surface, right? You cut the gap, so along this gap, you don't have the free current densities. So this case number 4, Js free is equal to 0. But you might be wondering, well, Professor, didn't you tell us you can have the induced magnetic dipoles, right? So I'm showing you in the direction of my externally applied field, I can induce perhaps one magnetic dipole. I'm drawing the cross section, right? This current is coming out, this current is going down, right? This forms a dipole, right? Forms a dipole, and therefore the dipole generated field is also parallel to the externally applied field. So then you ask yourselves, well, can this induced magnetic dipole give rise to a non-zero current density? Because from example number 3, you know that whenever you have a non-zero surface current density and it's big enough, you can swing the angle to negative, right? Forming self-closed loop. Self-closed loop. Isn't that what we're looking for? Right? This is my incident angle, and this is my exit angle, right? So now my theta 2 is negative, so it forms a self-closed loop. But think about it. If you form a closed contour across this induced dipole, you invoke Ampere's circuital law. H dot dl is I free, right? When you take the closed loop, what is the net current that you encompass in this case? One is going out, one is going down. They're equal in magnitude, reverse in direction. So, in this case, you cannot encompass a non-zero current density. Okay? Therefore, it's more like this case, right? More like this case. On this end facet, the fields come out. On the other side, it cannot form a self-closed loop. Okay? So even in this case, it is possible to have the field lines not re-entering it is possible that one of the field line does not re-enter the core, but in this way. Why? Your exiting angle has to be on the other side of the surface normal. So this field line does not re-enter the core, which is called the leakage, but it cannot form a self-closed loop. Because along this facet, you do not have non-zero free surface current density. Okay? So what I can tell you is the last slide contains all the essence that you really need to understand about magnetic materials. These 4 cases, you need to investigate and digest them in details and try to link the fact having non-zero J is very critical for generating self-closed leakage flux lines. All right? So with that, I close the second PowerPoint set. Next Monday, we're going to move into the very last PowerPoint set for magnetism, which is very short. So definitely we will finish magnetism next week. Okay? Questions? I'm having a good time explaining this slide, as you can see. So, well, if you have questions, feel free to ask me after the class. See you next Monday.